Welcome. In this video, we will be looking into ethylene and various chemicals obtained from ethylene. This video has the following content. We will be looking into the following topics for the next few minutes. Now, we will be looking into the polymers which are derived from ethylene. Polythene produced under different conditions show variations in its physical properties. Based on the densities, polythenes are classified as low density, high density, linear low density and very high molecular weight polythenes. The different physical properties which vary for different classes of polythenes are densities, crystallinity, melting points, and the ability of polythene to elongate at break point. Let's see into low density polythenes first. They were discovered accidentally by Fawcett and Gibson in a process meant for obtaining rubber. LDPE is produced at 2000 bar pressure and 200 C temperature and is a free radical reaction, thus not requiring any catalyst. LDPE is a highly and irregularly branched homopolymer with a density of 0.915 gram per cc. It has low crystallinity, low melting point, lower tensile strength due to lack of close packing between molecules. Process conditions are varied according to the type of polymer required. To control the degree of branching in LDPE, one should reduce the per-pass conversion, recycle the monomer and reduce the residence time. To obtain highly branched polymer, batch autoclave process is used. For controlled branching, tubular PFR with recycle is used. Continuous processes are preferred since heat of reaction can be removed continuously. Next polythene is high-density polythene, that is HDPE. It was discovered at Standard Oil of Indiana at Zletz. It is a heterogeneous polymer with 1-butene as comonomer along with ethene. For obtaining highly linear polymer, Ziegler or Phillips catalyst is used. Operating conditions are 1 to 300 bar pressure and up to 60 C temperature. HDPE is an extremely linear polymer with close molecular packing and density of 0.965 gram per cc. It is rigid and stiff but brittle at breakpoint and has high tensile strength, high melting point and 95% crystallinity. Since it is a linear polymer, there is no need to control branching. HDPE can be produced under batch or continuous conditions in autoclave, tubular, fluidized, bed or slurry reactors with 100% per pass conversion. Energy demand for HDPE production is less, but it's compensated by high cost of comonomers. Comonomers used in HDPE production are obtained by oligomerization of ethylene or by fractionation of crude. Comonomers obtained from refineries by fractionation cost less compared to comonomers obtained from ethylene. Next polythene is LLDPE or linear low density polythene. It is a heterogeneous polymer first produced in US. It has properties intermediate between LDPE and HDPE. The operating conditions are similar to HDPE. Comonomers are also used for LLDPE production like 1-butene, 1-hexene, or 1-octene. LLDPE is a linear polymer having density and crystallinity identical to LDPE. It has higher tensile strength compared to LDPE but less than HDPE. LDPE is used in molding and extrusion processes. The last of the categories of polythene is very high molecular weight polythene. It is a homogeneous polymer synthesized under operating conditions similar to HDPE and having density of 0.941 gram per cc. It is used for manufacturing ropes, ski bottoms, cables, cable nets, body armors. Dyneema, as called in USA, is a polymer produced by DSM process and has tensile strength 15 times that of steel. Dyneema is abrasion resistant. It is hydrophobic and absorbs waxes due to its porous structure. It is not very prone to creep. It has high tensile strength and can be easily drawn into fibers. Dyneema is produced by sintering to give uniformity. Let's have a quick revision of what we have learned till now through a question and answer session. Let's see if you can answer these questions. So, the first question is, What are the three major types of ethylene polymers? And the answer to it is LDPE, HDPE, and LLDPE. Next question is catalyst necessary for polymerization? And the answer is no, catalyst is not essential. Polymerization can occur as a self-sustained free radical mechanism in presence of oxygen as initiator. Let's move on to next question. What is a major difference between LDPE and LLDPE? LLDPE has regular branching whereas LDPE has highly irregular and higher degree of branching. So, were you able to answer these questions? Let's see if you can match the polymers with their respective applications. And, the correct matches are Now, let's have a look into copolymers of ethylene. Ethylene is found in many other copolymers, but all of them are sold in comparatively low volumes than HDPE, LDPE, LLDPE. One of the earliest of copolymers is chlorosulfonated low-density polyethylene hypalon, which is an elastomer formed by chlorosulfonation of polyethylene with sulfur dioxide and chlorine, leading to insertion of SO2Cl and Cl groups into the chain. It is prized because of its ozone and oxidation resistance. It is used in gaskets, wire and cable installation, roof coatings, white sidewall tires, and coated fabrics. Ethylene vinyl acetate is a random copolymer with two types of textures: hard and rubbery. Less than 50% vinyl acetate makes EVA hard and suitable for adhesives or membrane production, while more than 50% makes it rubbery and is useful for water-based paints. Ionomers are special class of copolymers containing ionic groups like pendant carboxyl groups. These groups have the ability to form cross-linked polymers by their interaction with mono or divalent metal ions to give carboxylates. Unless heated, these types of polymers cannot be processed due to strong cross-linking. Their thermoplasticity makes them useful. They are used in production of ski boots, flexible hosing, and coating of golf balls. A tougher class of ionomers finds applications in manufacture of bumpers and body panels of automobiles. Ethylene-propylene copolymers containing 20 to 80% ethylene are called non-crystalline elastomers, or EP rubbers. These elastomers find specialty uses where long service life is required, particularly for roofing, as also in automobiles for gasketing, belts, hose, wire and cable coating, and under the hood applications where high temperature resistance is required. Materials with density as low as 0.89 gram per cc were classified as ultra-low dense by Union Carbide in 1980s. Ultra-low density polythenes are a type of these material characterized by low stiffness but good tensile strength. The plastic, which can be degraded in presence of light, is a promising solution to all plastic waste. This feature can be incorporated in the polymers by copolymerization of about 1% of carbon monoxide to give ketone groups in the polymer chain, which are degraded by ultraviolet light below 350 nanometers. Ziegler technology has made the otherwise uncontrollable process of ethylene oligomerization feasible. It is uncontrollable mainly due its free radical mechanism. Catalytic conversion of ethylene to 1-butene or 2-butene is a dimerization reaction. 1-butene formation is catalyzed by bis, 1,5-cyclooctadiene, nickel, triphenylphosphine and para-toluene sulfonic acid. 2-butene is more stable and its formation is catalyzed by tri-N-butylphosphine nickel dichloride and ethyl aluminum dichloride. Ziegler oligomerization of ethylene involves conversion of triethyl aluminium to trialkyl aluminium at 100 degrees centigrade and 100 bar pressure, where trialkyl further reacts with oxygen to give alkoxide. This alkoxide can be hydrolyzed to obtain straight-chain alcohols. Under separate process conditions of 280 to 300 degrees centigrade temperature and 50 bar pressure, trialkyl aluminium can be converted to alpha olefins. A broad distribution of molecular weights is a major drawback. SHOP is an oligomerization process devised over nickel catalyst by Shell, carried out at 100 degrees centigrade and 40 bar pressure, giving majorly alpha olefins from C4 to C40 with discrete distribution of products. The process is described in the next slide. The major steps involved in SHOP are: initial formation of C10 to C14 fractions, separation from rest mixture by distillation, linear hydroformylation of C10 to C14 alcohols to C11 to C15 alcohols over rhodium catalyst, heterogeneous oligomerization of C4 to C10 and C16 to C40 alpha olefins, obtaining 10 to 15% of desired chain length by metathesis and fractional distillation, and use of cobalt catalyst to hydroformylize internal alpha olefins. It's question and answer time. One of the earliest is chlorosulfonated low-density polyethylene is known as what? Answer is, hypalon. Next question. Depending on the proportion of vinyl acetate, it may be either what? It may be either hard or rubbery. Match the following copolymers with their respective applications. This is the answer. Were you able to answer the questions? Let's look at vinyl chloride now. Vinyl chloride is an organochloride with molecular formula C2H3Cl and is a monomer of PVC, which is polyvinyl chloride. So, how is vinyl chloride synthesized? First industrial method of producing vinyl chloride was by hydrochlorination of acetylene. But, nowadays a newer method is used to produce vinyl chloride, which is used by most industries. In this method, ethylene chloride is formed from ethylene and chlorine, which when heated in contact with pumice or charcoal yields vinyl chloride. Vinyl chloride is used mainly in manufacture of polymers like PVC. It is also used as a starting material for various other products as mentioned. Now, we will learn a few things about acetaldehyde. Acetaldehyde was originally from acetylene made by its hydration over mercurous mercuric sulfate ferric sulfate. In the early 1960s, the above route was displaced by the oxidation of ethylene-based ethanol at 450 degrees Celsius and 3 bar with air over a silver gauze catalyst. Acetylene is mainly used as a precursor for the producing various other chemicals such as acetic acid, pyridine derivatives, croton aldehyde, and penterythritol. Next is ethylene oxide. It is synthesized by direct reaction of ethylene with oxygen over a silver catalyst. More oxidation of ethylene and ethylene oxide yields carbon dioxide and water as byproducts. Due to advances in catalyst technology, there has been an increase in yield of ethylene oxide. It is important to have high selectivity for ethylene oxide formation to cover up for the raw material cost of ethylene. Initially, selectivity was 65 to 70%. But with improved catalysts, selectivity increased to over 90% with 82% as average selectivity. Shell, Dow Chemical, and Halcon have patents for these technology. Addition of minute amounts of potassium, rubidium, or cesium ions to the silver catalyst increases yields according to a patent by Shell. Ethylene oxide and starch or cellulose react to form hydroxyethyl derivatives, which is a thickener for water-based paints and protective colloid for water dispersions. Other major uses of ethylene oxide include reactions with alkyl phenols, fatty alcohols, amides, and amines to yield non-ionic surfactants. Ethylene glycol. How is it prepared? It is prepared by hydration of ethylene oxide, where excess water is used to prevent the formation of higher ethylene glycols. Purification of ethylene glycol is done by repeated fractional distillations to separate the glycol from its oligomers. It is used for preparing polyester resins. It is majorly used for preparing polyethylene terephthalate or PET, which is used for synthetic fibers production, which is a potent product obtained from ethylene. Yes, it's ethanol. Let's now learn more about ethanol. Ethanol is commercially important as a solvent, alcoholic beverage and as a future source of renewable energy in form of biofuel. Let's have a look at the various processes for ethanol production. It was first produced in 1930 by reaction of cold concentrated sulfuric acid over ethylene. At high temperatures, diethyl ether, an important solvent, was obtained as byproduct. It has good selectivity for ethanol under appropriate temperature modulated conditions. This method was replaced by direct ethane hydration over phosphoric acid catalyst at high temperature and pressure. But, the reaction at high temperatures favored formation of ethane and water. Hence, recycle of reactants is necessary to keep low per pass conversion. Ethene was obtained either by dehydration if ethanol or by steam cracking of crude. The latter was a cost-effective option. Complete synthesis of ethene was much costlier than refinery process. In general, ethanol produced by any method needs to be purified to obtain high purity and hydrous product. Azeotrope of water and ethanol is major challenge to be overcome, as breaking of azeotrope either by distillation or counter-current extraction using other component is energy intensive. As stated earlier, ethanol is a versatile molecule and finds varied applications majorly due to good solvating properties, attributed to hydrogen bonding, potability and calorific value. It is used as a raw material in acetic acid, acetaldehyde, ethyl acetate, vinegar production. Gasohol obtained by its aerobic fermentation is a good biofuel and major area of ongoing research to obtain it from corn stover. Do you know? Hydroformylation of formaldehyde in the presence of a homogeneous rhodium catalyst. What is name of the process? It is Monsanto process. Did you know this? Textile fiber name which is synonym with terylene is. It's Dacron. What is the previous name of the famous company Huntsman? Huntsman was previously called as Texaco. Which country had started commercial production of Buna S rubber in 1938, which was very important for war? The answer is Germany. Do you know the three methods to break ethanol water azeotrope? They are: azeotropic distillation, counter-current extraction using benzene to break the azeotrope, pervaporation membrane technology. So, did you know all these? Next, we will be looking into the major chemicals obtained from ethylene. Styrene, vinyl chloride, ethylene glycol, and vinyl acetate obtained from ethylene are monomers for various different polymers. Ethylene oxide is used for ethylene glycol synthesis and in polymers and as an antifreeze. Ethanol was used as a raw material of acetic acid prior to advent of Wacker process. Ethylene glycol is used as a monomer for PET, that is polyethylene terephthalate synthesis. Methyl and ethyl glycol ethers were found to be teratogenic and hence banned. New major chemical from ethylene is alpha olefins, which are mostly converted to fatty alcohols. Fatty alcohols as ethoxylates or sulfates are used in surfactants for detergents. Alpha olefins are also used as comonomers in LLDPE and HDPE production. Trimer of 1-decene is a synthetic lubricant. Alpha olefins are converted to alcohols by hydroformylation and are used in surfactants or for plasticizers depending on number of carbon atoms present in alcohol. LDPE is being replaced by LLDPE. But, LDPE is used in combination with LLDPE for certain applications, and it is also essential for extrusion coating of paperboard for milk and juice cartons. Now, we will look into chemicals which are produced in less quantities from ethylene. Two of these are propionic acid and propanol, which are produced by hydroformylation of ethylene. The various conditions and catalyst required for hydroformylation are described. Propanol is used as a solvent in inks, production of esters, acids under specific conditions. Cook reaction for formation of propionic acid from ethylene by carbonylation has been described. Presence of ethylene is necessary for chlorination of ethane. Ziegler-Natta catalyst is a combination of triethyl aluminium with titanium salts. Triisobutyl aluminium is sometimes used as an alternative for triethyl aluminium in Ziegler-Natta catalyst. Ziegler-Natta catalyst is a combination of triethyl aluminium with titanium salts. Triisobutyl aluminium is sometimes used as an alternative for triethyl aluminium in Ziegler-Natta catalyst. Ethylene is also used to produce diamines. To prevent the formation of tetra, pentaamines, reaction is carried out in liquid phase with excess ammonia. Vinyl chloride is also obtained as a byproduct in this reaction. Diamines formed are then used for synthesizing diethanes, a fungicide, and EDTA, which is a chelating agent. Hydroxyethylaminoethylamine, which is used as a textile finishing agent and epoxy resin curing agent, is also produced from ethylene diamine. We will be looking into derivatives obtained from ethylene derivatives now. We will start with ethylene oxide or EO. The derivatives obtained from ethylene oxide include oligomers of EO, glycol ethers, glycol esters, ethylene carbonate, ethanolamines, and 1,3-propane diol. Next is ethylene glycol. The derivatives from ethylene glycol are glyoxal, cyclic acetal, 4-hydroxyphenylglycine, dioxylane, dioxane, and ethylene glycol dinitrite. Vinylidene chloride and tri- or tetrachloroethylene are derived from vinyl chloride and ethylene dichloride respectively. Ethylene dibromide is produced by direct bromination of ethylene. Ethylene dibromide on dehydrobromination gives vinyl bromide. With sodium cyanide, it gives succinonitrile, which on hydrogenation gives 1,4-diaminobutane, which is used to produce nylon 46. Ethanol derivatives include ethyl ether, ethylamines, atrazine, which is an herbicide, and disulfiram. We will now have a final review of what we have learned in the last few minutes. So, what are the oligomers formed by hydrolysis of ethylene oxide? Oligomers are diethylene and triethylene glycol. Are oligomeric polyethylenes water insoluble? No, they are soluble. How do oligomeric compounds reduce viscosity of water? They do so by reducing their hydrogen bonding. The ethylene glycol monomethyl and monoethyl ethers and acetates have been found to harm the reproductive and development process in mammals. Why? Branched structure from glycol ethers reduce the sperm count. To obtain aminoethyl alcohols using ethylene oxide with ammonia. What are the operating conditions? The operating conditions are aqueous ammonia at 100 C and 100 bar. Which company developed a catalyst that combines syngas with ethylene oxide to give 1,3-propanediol in high yield? It shall. How can ethylene glycol used as freeze inhibitor? It can be used as a freeze inhibitor by nitrating it to form ethylene glycol dinitrate. Thank you for viewing our video. Hope you enjoyed it and learned a lot from it.